morning, welcome. I'm Hilary Weinberg, your host, and this is Research in Manoa. I'm filling in for Jay Fidel today. And I have here Sarah Fagents, who's a professor of Planetary Volcanics at UH Manoa. And we're really excited to have her on the show because we're talking about some stuff that's not only relevant, because we're going to be talking about the Mars mission, but interesting and relevant to Hawaii and all these different controversies and things that are going on. So we're happy to have her here. Welcome.
Thank you.
So what brought you here, and what brought you to Planetary Volcanics? Like, what was that road?
Well, I did my bachelor's in the UK in geophysical sciences at a time when the oil industry was in a bit of a difficult state. And I realized I was being trained to do seismic data processing, sitting in front of a computer, processing signals, and I didn't really light my fire very much. But luckily, there was a professor at my university at Lancaster in the UK who was very inspiring. He studied volcanoes on the Earth and on the planets, and I got to work with him a little bit, and he offered me a PhD position. I took that. I did my grad school there, and that sort of launched me into studying volcanoes on the Earth and other planets.
Wow, so what is it about volcanoes that interests you?
I think it's, they're so alive. They're creating brand new, fresh planet Earth. We can go out to the Big Island here and watch the lava flowing and creating new ground, new territory, and it's just the most sort of vibrant aspect of geology to me. I was always interested in geology, in looking at the world around me and understanding or trying to understand how it got the way it was. But most of geology is looking at old rocks. We've got a lot of old rocks in the UK. And what really lit my fire was looking at, literally, the hot new rocks being formed. And I just found that completely fascinating.
So was there anything when you were little that was drawing you to geology that you could have, predicted that you would be doing this? Because this is something that never really occurred for me to study, but it's so interesting and such a varied, deep field.
Yeah, I mean, I had the sort of typical kid-like fascination with dinosaurs and volcanoes and stuff like that, but I didn't really actually realize you could get a job doing volcanoes for a living. But just as I worked my way through academia, it became more and more, possible. I realized that I could actually specialize in studying volcanoes, and it would take me to amazing parts of the world. And if I figured out that if I could get somebody to pay me to do that for my living, then I'm going to do that.
So tell me about the first time. What's the first volcano you saw, and what that experience was like, bringing the classroom to the real world?
The first volcano I saw in the flesh, so to speak, was actually Kilauea. As part of my graduate studies, I came out to Hawaii back in 1990, I think it was, with my advisor to do some field work out there. And Kilauea sort of shattered my illusions of what volcanoes are. I mean, you think of your archetypical volcano with the steep sides and the bubbling cold air at the top, but Kilauea is this very gentle, very tame volcano that you can really get right up close to and look at. So Kilauea was the one that really first inspired me.
Oh, so that must have been so exciting when you got the position here.
Yes. Fast forward a few years, and I always knew that I'd love to come back to Hawaii. And after I finished my PhD, I did some postdoctoral work in various places, Washington, D.C. and Arizona State University. But I was just waiting for the right position to come up, and then the position opened up here, and I applied, and couldn't quite believe my luck when I got the position and I was able to move here. And
lo and behold.
Yeah.
So how often are you at active volcanoes now doing field work?
Typically several times a year over to the Big Island to go and do work out there. And then I also have projects in Iceland, New Zealand. Those are the main two focuses, and I typically get there once every couple of years, depending on the grant cycle and what funding I've got for field work. It's been probably 3 years since I was last in Iceland, but that's a key place for studying volcanoes that have analogs to volcanoes on Mars, for example. There's a lot of cool stuff in Iceland that we can look at and understand a little bit more about Martian volcanoes as a result.
So that's, okay, this is a really great, easy transition. So what is it, what are the qualities of Mars that make it different than Earth? Just kind of like basic science lesson. Right. And then what is it about Iceland that mimics them?
Right. Mars is further away from the sun than the Earth. It's smaller. and it's a colder environment. It has a low gravity because it's quite a small body, and it has very little atmosphere. It's lost most of its atmosphere. We look at the surface of Mars, we see a very arid, cold environment. Now, Iceland has volcanoes that have formed in cold environments. It has certain surface features that look very similar to the surface features we see on lava flows on Mars. We look at Mars and we see volcanism everywhere. But starting in about the 1990s, we started to get images back from the sort of latest era of Mars spacecraft that showed in very fine detail the surface features of lava flows on Mars. And one of the features that I'm particularly interested in is something called rootless cones. These are cone-like features that look like the cinder cones we see on Big Island. But they form on top of lava flows, and they form when lava flows flow over a ground surface that has ice or water in it. And they have, the lava interacts with the water and it causes explosions, and the explosions create these cones out of the lava that's excavated from the explosion site. Now, you can see on the image here, this is a picture of some of these cone features on the surface of a lava flow on Mars. On the left-hand side, we see there's hundreds of these things on an old lava flow surface. The right-hand side is a zoomed-in version of one of these cones. And they look very similar to cinder cones that you might see, especially on Mauna Kea, for example. Now, we see very similar features formed on top of lava flows in Iceland. And that's what first sent me to Iceland, to go and study these cone features in detail. In Iceland, we have lava flows that interact explosively with lake water or marshy ground. Now, the difference between this kind of cone and a cinder cone on Mauna Kea, for example, is that this forms where the lava flow is flowing over the surface, these rootless cones, and you get explosions because of the interaction of the lava with the water. A Mauna Kea cinder cone, and most cinder cones, form as a result of magma coming up a vent rooted deeper in the crust. So the reason we call them rootless cones is because they don't have this volcanic vent root.
Okay.
They're purely surface features that have been formed by interactions with surface water. So that's what sort of first took me to Iceland, basically.
So is there some sort of liquid on Mars that's creating these rootless cones?
We look at the surface of Mars and we know that there was, in the past, a lot of water, and that water created massive outflow channels. We see features that can only have been produced by water. But this was in the past. This was, 3 to 4 billion years ago. Mm-hmm. We don't see evidence for such a large-scale water on the surface now. And that's because the atmosphere has declined over time. It can't keep water liquid at the surface. It either evaporates or it's frozen. So currently, water exists on Mars in the subsurface or very, very near to the surface in some cases, but in ice form. So the features we see on Mars, we know formed a long time ago when those lava flows were active. But nowadays, the water is buried as ice, and also we don't see active volcanism on Mars currently. Okay. But we know at the time that flow formed, there was water available for the lava to interact with. It may have been in ice form, but the lava probably first melted it and then vaporized it to form these explosive features.
So is that one of the ways that they figured out that there was water on Mars?
Yes, yeah, you can look at, there's a whole host of different types of geologic feature that you can look at, and by analogy with our experience on Earth, and this is where terrestrial fieldwork is really vital to understanding the other planets. By analogy with our experiences on Earth, we know that we can look at a particular feature and say, oh, that must have formed when there was water there. The other lines of evidence that we have that there was water at the surface of Mars is from the orbiting spacecraft that are up there now, we can take snapshots of the surface of Mars in different wavelengths. Like we have cameras with different filters on that can look at the response of a target surface in different wavelengths of light, and different minerals have very different characteristic responses in different wavelengths of light. And by looking at the responses, it's like a fingerprint of a particular mineral. And there are particular minerals that form only under aqueous condition when water is present. So we can look at the geology, look at the features and the shapes of the features that we see and understand they must have formed with water. Or we can look at the composition of the surface and understand if we see particular sets of minerals, we know that must have formed in the presence of water.
So what was it, were you part of the team that first realized that these features must have been made by water, and what was that like when you found out that research, these results were coming in? That must have been so exciting.
Yes, it was, I can't lay claim that I was the first person to see these things and say that was water, but I was working at the time at Arizona State, and my boss at the time was Ron Greeley, who's a preeminent planetary scientist. He died a few years ago, unfortunately. And one day he just gave me an image with these cone features in and said, these look like pseudo-craters or rootless cones in Iceland. Why don't you work on this? And so that sort of set me along the path. There was another team at University of Arizona who were also looking at these features as well, and we sort of collaborated along the way.
Wow, that's great. So what is the most exciting part of this specific research? Where do you think it's going, and what are you hoping to find out down the line?
Okay, our current line of research is very much focused on fieldwork in Iceland. We know that when magma meets water, something explosive happens some of the time, not all of the time. A case of something not explosive happening is you go to the Big Island when the lava is flowing into the ocean. Most of the time, it goes into the ocean very quietly, without very much in the way of fireworks. But every so often, conditions are right that explosions happen. And we've seen explosive eruptions at the coastal entry on Kilauea numerous times over the last few decades. So what we were trying to get at is what are the conditions that lead to explosive interactions? On the large end of the scale, we know that even eruptions that are coming up primary conduits from deeper in the crust, if they interact with near-surface water, that water can enhance the explosivity of that eruption. It helps to, as magma is rising, it has gases dissolved in it, and as it gets closer to the surface, these gases form bubbles, and eventually these bubbles will rip the magma apart, which is when you see these ash clouds coming out of volcanoes. That can explode in the absence of any external water, but if you add external water to the mix too, it gets even more explosive. The particles that are produced are much, much smaller, and they are able to give that heat to the gas. The gas then streams out of the vent, and you see these very, very tall eruption columns. So we know over primary vents, water makes much more explosive eruptions, and they're very hazardous.
This is all very exciting stuff. Unfortunately, we have to cut to a commercial break. We'll be right back. Please join us on Twitter at ThinkTechHI. We'll see you in a minute.
Hi, I'm Ethan Allen. I host Likeable Science on ThinkTech Hawaii, and I do this because I care about science literacy in Hawaii. I want to spread the understanding that science is a vital and interesting part of everyone's life. I want to make sure the broadest possible spectrum of people understand the beauty and the value of science and realize that science plays out each and every day of their lives. I want you to understand that science is fun. So we bring on to this show each week guests who are scientists, from astronomers to zoologists, and we talk about what they do and how they do it. But most importantly, we talk about why you should care about their work, why you should see that their work has value and impact on your life. So I hope you'll join us Fridays, 1 p.m. here on ThinkTech Hawaii. You can watch us via live stream. You can watch us recorded on Olelo, and you can see us each week. We hope you'll join us.
Welcome back. This is Hilary Weinberg. I'm a guest host for Jay Fidel. This is Research in Manoa, and I'm here with Sarah Fagents, who's a professor of planetary volcanics at UH Manoa, and we're so excited to have her here because she is working on the Mars mission and water on Mars and magma, and being able to deduce all these really interesting things from her studies. So before the break, we were talking about what happens when magma and what hits water. And we're going to go back to that a little bit and discuss this a little more detail and why this is important.
Yeah, so before we were talking about what happens in a primary eruption when an eruption is coming up through a volcanic vent. And we have gases that are dissolved in the magma plus external water that can create very explosive eruptions. Now, when we look at the rootless cones, the examples in Iceland we can go out into the field and look at, We know that it doesn't have any more the gases contained in the magma. It's been flowing as a lava. It's had plenty of chances to lose its own gas. So the only way that's going to explode is if external water is involved.
Okay.
And the way these things work is you have a lava flowing along. They are typically pahoehoe type lavas, so very similar to the lavas that we're seeing at Kilauea right now. So they flow along and they cool at the surface and at the base very quickly. So you don't see the glowing red lava, but inside there's lava, molten lava still flowing. And so the way a pahoehoe flow field advances is it advances quite slowly. It'll break out here and break out there, and over months or years it will form a large flow field. Now in Iceland, these flows enter marshy areas or wet areas, and because it's got this basal chilled crust at the bottom of it, it doesn't immediately explode. But as the lava starts to sink down into the sediment of the lake, it can crack at the base, and then the very hot molten lava from the core can come into contact with the water, and that's when you can get these explosive dynamic interactions. The water flashes to steam. We can see here are some examples of these cones in Lake Mývatn in Iceland. These are some beautiful cones in the foreground here, each of which will have been like an explosion center as the lava flowed into this lake. And as the explosion proceeds, the magma, the lava, and the water mixes. The lava shatters into smaller and smaller pieces. It produces a lot of steam under pressure, and then it blasts through the overlying lava flow, excavating fragments of lava, which then sort of fall out around the explosion site to produce these cone-shaped features such as you see here.
Wow, and is that how islands are created?
In this case, I mean, you can get small islands forming in the lakes. It's usually a shallow water environment that the lava flows into. And you can see they form absolutely beautiful, beautiful landforms here. Now, as I mentioned before, the lava flows lost all its gases. Now, if we dig into these cones and look at the deposit itself and at the particles that make up the deposit and look at them under microscopes or in thin section, there are characteristic traits that these particles have, shapes and surface textures that are diagnostic of the fact that external water was involved and not dissolved gases from the source. So what we're currently doing, or what we have been doing out in Iceland, is looking at the deposit in like excruciating detail to figure out what exactly the shapes and textures are that are indicative of such an interaction. Then we can take our results from this study and compare them to eruptions from primary events when water and dissolved gases were involved, look at those particles in minute detail, and figure out just how much more enhanced the explosivity of that eruption was based on how much water was involved, based on looking at the particles that were thrown out in that eruption. Yeah, it takes a long time to explain because it's very detailed work.
Yeah, it is, and that's, so what keeps you going with this work? I mean, what are you hoping, what are your dreams for this field?
The bigger picture of this work is to understand how water affects explosivity and to ultimately contribute to mitigating the hazards posed by such explosions, by such eruptions. You can see here, this image is a cross-section through one of these cones. This is at a group of cones called Rootless, just outside of Reykjavik in Iceland. And this area was extensively quarried. This is my collaborator, Christopher Hamilton, in the foreground there, taking pictures. This area was quarried, so we have nice cuts through the center of these cones. And you can see there's layering in this cone here, and we can tell a lot by measuring the different layers, by digging samples out and looking at the particles. And layer by layer, we can figure out how this cone was built up by multiple explosions as lava continues to feed into the explosion site and keeps on interacting with the lake water underneath it or the wet sediment underneath it until basically it dries the area out. And towards the top of this cone here, you can see there's a kind of a solid cap, and that indicates to us that towards the end of the eruption, there was very little water being vaporized to contribute to these explosions. So the lava was barely being torn apart. It was just being sort of heaved out onto the side, and it was still hot when it landed. So it produced this welded sort of lava flow-like cap to the top of the cone. Yeah, to get back to your question though, yeah, the idea is to really understand how water enhances explosivity of eruptions and help to mitigate the hazards. We know from experience that these highly explosive eruptions can shut down airspace for weeks at a time if the ash gets into the wrong part of the atmosphere, basically. And understanding how these volcanoes work can help us to prepare for future eruptions in terms of who we need to notify, what sort of area will be impacted by such eruptions.
Yeah, that's interesting work. I once watched a documentary on the effects of that big eruption in Iceland several years ago and the effects it had on global industries. I mean, from the flower industry in South Africa, how it kind of crippled that industry for months.
Yes.
All different, I mean, you know, that's something that we wouldn't even think about, but yeah, there's all these flowers and you freeze them and you ship them to Europe and there's all of these different things that are affected and the global economy is so close that this is very important stuff.
Yeah, it has a lot of knock-on effects that you wouldn't necessarily think about right off the bat.
So what are you finding? So, you know, we saw that picture, there's that the cap, and then there's that stuff in the middle. What are you finding that that's composed of? And what does that knowledge bring anything to the scientific table, or?
Yeah, we're finding that much of what we see in that section, for example, is lava that was torn up into particles of various sizes and thrown out of the vent. But the red color you see here, actually Rothalar is Icelandic for red hills. The red color you see here is actually not oxidated lava, but it's mud, lake sediment that was involved in the explosion and baked to this red color. So what we take home from that is that these explosions are incredibly dynamic. The lava meets the sediment, and it's not just a case of vaporization and sort of a steam bubble bursting out. It's really vigorous, dynamic mixing between the lava and the substrate. And this kind of explosion has an analogy with industrial molten fuel coolant interaction explosions. So we know that there's a lot of mixing going on. It's a very dynamic event, and so we have a natural example of molten fuel coolant explosions, and we can use the theory that was developed in industry to try and understand the pressures that build up and ultimately to understand how far this material is distributed and how hazardous it is.
So, and that same type of information, what does that say about what's going on Mars with these cones? I mean, have you been able to get any samples from Mars, or is there is there anything you can kind of extrapolate from what you see about what must be happening underground, or what? I mean, I don't know. Just tell me what's going on.
Yeah, no, definitely. We use our experience with these Icelandic cones to inform our interpretations of the Martian features. So by looking in great detail at the Icelandic features, we are starting to get a grasp on how much water must have been involved. We look at the Mars surface, we can measure the dimensions of the cones, we know how big their craters are, we can calculate the volumes of them, and based on our terrestrial experience, we can then, with some modifications for the different environment, the different gravity and the atmospheric pressure, low atmospheric pressure, we can use the models that we have on Earth and adapt them for Mars and work back to figure out, okay, so how much gas must have been involved in this explosion to send material out so far on the Martian surface to build a cone of this size. And it turns out that because Mars has such low gravity and low atmospheric pressure, you really don't need much water.
Oh, okay.
So it could quite happily exist in the pore spaces of the ground underneath the lava flow as ice, and the lava flow just melts it, vaporizes it, and blasts it out. So it's giving us an idea of where, when, and how much water there was on Mars in these particular areas.
Yeah, because I was imagining, were there oceans on Mars ever? Was there large bodies of water? And, you know, of course, then the question of, could there ever be life forms, or the way we understand life forms of needing water and the way they're created?
Well, that's the key question. That's what NASA is seeking to find out with the Mars missions there. There are theories that there were large oceans on Mars, but we know for sure that there were large lakes housed or hosted within impact craters on the surface of Mars. The Curiosity rover just a few weeks ago found evidence that there had been a long-lived lake within Gale Crater where it's roving around at the moment. That was announced just a few weeks ago. So we know, we can look at the surface, we see these large-scale channels, we see morphological or geological signs that there was water, but now the Curiosity rover has proven that there were long-lived standing bodies of water. And these are environments that are potentially habitable by microorganisms.
So then, going back in time when there was greater atmosphere, more atmosphere, when there was an atmosphere on Mars, did they have water cycles like we have, where, when it got hotter, it came up and there's clouds and it rained and the water moved around like that?
Yeah, in some models there's snow and precipitation in general. And yes, it would have cycled through with the seasons and with the tilting in the axis of rotation of Mars. There would have been water moving around here and there and everywhere. And we currently see similar effects with the carbon dioxide ice caps on Mars. The carbon dioxide moves around in cycles as well, seasonally.
And then, is there ways to tell, well, because then the temperatures would have had to be different. They would have had to have, a certain degree of temperature. You're saying it's a colder planet, but for there to be liquid water, it would have had to be warm. Do you think the conditions for it to be liquid water came only from the magma, or do you think the atmosphere created a warm enough environment for that?
Yeah, back in the past, like 3-4 billion years ago, with there being a thicker atmosphere, that keeps water stable at the surface. So it was also warmer as a result, warmer and wetter. Now, because the atmosphere is so thin, even in the areas that warm up in the summer, water isn't stable in liquid form. It wants to just evaporate away. And that's because the atmosphere is so thin, it can't keep, there's not enough pressure to keep water liquid. So in the past, yes, theoretically with a denser atmosphere and warmer climates, there would have been, a period of time when substantial bodies of water could have existed, and those are the areas that could potentially have been habitable.
This is exciting. This is really cool stuff. This is cutting edge research. So unfortunately, we have to do another commercial break, but we will be right back, and then we can talk more about this.
Okay.
You can get to us at Twitter at ThinkTechHawaii, at ThinkTechHI. We'll see you in a minute.
Hi, I'm Jay Fidel. I'm host of Hawaii, the State of Clean Energy, which is our flagship show, which plays 4 to 5 p.m. every Wednesday. And the supporters of that show are Hawaii Energy Policy Forum and Hawaii Energy. And luckily enough, we have representatives of both of them right here today to tell you more about what they think about the show. Sharon Moriwaki at my left is co-chair of Hawaii Energy Policy Forum, and she goes first. Sharon?
Thank you. Thank you, Jay. I'm so glad that we have this Hawaii, the State of Clean Energy. This was 2 years ago when we started this, and we have continued it because it's so important, and there's so many developments happening across the state, and we hope you'll tune in every Wednesday, 4 to 5. It's wonderful.
And Ray is Hawaii Energy. Ray, what is your thought about the same subject?
Well, I agree completely with Sharon that we are talking about every Wednesday, 4 to 5. We talk about some of the most important subjects that are affecting the islands now and into the future. Energy, clean energy, we need it. We often run into new ideas that we had not thought about before. We did just today, and I think we're going to have more of that in the future. So come on down and watch us 4 to 5 on Wednesdays, and we'll see what happens.
We'll see you then. Aloha.
Aloha.
Welcome back to Research in Manoa. I'm your guest host, Hilary Weinberg, and I'm here with Professor Sarah Fagents, who is a really exciting professor at UH Manoa looking at planetary volcanics, and she's involved in the Mars 2020 mission. We're so excited about all of this. So Sarah, when we cut to a commercial break, we were talking about water on Mars and how the atmosphere must have been different. Is it possible at all that there was any other types of liquids that were moving around on Mars? I mean, different combinations of chemicals and become different liquids, but how do we know it's water?
we look at the temperature ranges and pressure ranges that were likely to have been present, and that really sort of narrows things down. It probably wasn't pure water, like stream water or ocean water. It was probably very briny in some cases, especially when we have lakes forming within impact craters. As those lakes dry up, they leave behind a concentration of various brines that, as the water evaporates and goes away, chlorides, sulfates, things like that, we can see from orbit today with various instruments. So we have an idea then that, okay, there must have been a lake here, but it was with a great degree of certainty, water plus or minus other minerals dissolved in the water.
Okay, so let's take this, talking about briny water and all these different things. Let's come closer to home. What's happening do we see these types of volcanic forms in Hawaii, on Big Island, and what causes them, and what's going to happen?
Yeah, as I mentioned earlier, we do sometimes see, when lava flows into the ocean, explosions at the ocean entry. In some cases, lava is just very passive. It flows in, it produces pillow lavas, not much exciting happens. But under certain conditions, we see explosive forms. And the National Park and the Civil Defense are very careful to keep people away from these areas when they're active like that, because they are very hazardous. So something that could, on the one hand, be a very passive, non-dangerous experience can very quickly and unpredictably, and we don't exactly understand why, turn into something that's explosive. The image here shows a picture from the USGS, United States Geological Survey, Hawaii Volcanoes Observatory website that was taken, I think, in 2008, when there was one of these explosive ocean entries. You can see lots of particles, lots of blobs of magma, of lava being ejected from this explosion site. And again, over time, these kinds of explosive interactions build up these cones, so-called littoral cones, at the ocean entry. The previous image that was up on the screen showed some of these cone features down on the flanks, here we go, of Mauna Loa. We see the very black stuff is the lava flow, and then these little mounds, one in the foreground, one in the middle distance, are these cone features that were formed. So what my graduate student, Erin Fitch, have been doing is going and investigating these cone features, staying away from the ocean entry, staying away from the hazard zones, but looking at these features that were formed in the past. And again, we can do sort of detailed sort of analyses of these features, looking at the particles, looking at the shapes of these features, to understand how the water and the lava must have interacted to produce these cones, and try and figure out what the conditions are that lead to these explosive interactions, and help us just understand the hazards associated with such eruptions.
So what can you do with this information? How does this help the people of Hawaii and the state of Hawaii?
It helps us to basically know when to stay away from these features. I mean, you always need to treat the lava flows of Kilauea with respect, because even though they're slow moving, even though they're not, highly hazardous, it's very easy to get into trouble out there. So it helps us to understand hazard zones, how far to stay back, how far to keep visitors away. And by analogy, it helps us to understand the Martian case too.
That's great. So let's talk, what about, you said you have some work in New Zealand. Is this correct?
Yes, I was working in New Zealand up to a few years ago, actually, and this was a slightly different project. I was working on how to model the flow of volcanic mud flows, so-called lahars, that take place when water is released onto slopes of volcanoes. So, for example, Mount Ruapehu had a crater lake that was dammed at the summit of the volcano by a weak barrier of ash. And as the lake filled, eventually that barrier broke and the water flowed out of the lake onto the flanks of the volcano, picked up a lot of debris, and became a very fast-moving, very devastating, potentially devastating mud flow, volcanic mud flow. And so what I was doing at that point was trying to understand the physics of how these things move. Again, ultimately to understand what kind of hazards are posed downstream to communities as these flows inundate the flanks of the volcano.
So, you've done all these great projects in all these different parts of the world and even outside of the globe. Where does, the funding and the excitement and the, where does the motivation come from? Who's interested? Who helps you? What, resources are so important to this type of research?
Yeah, the work that we've been doing in Iceland on the Rootless Cones has been funded by the National Science Foundation. And they have a program, geochemistry and petrology, that funds volcano research. And they are always interested in the broader impacts. Okay, so how is this going to benefit society? Clearly, with understanding magma water interactions, there's a hazard aspect to that it's beneficial to society to understand the magnitude of that. National Science Foundation are also very keen on education outreach. So as part of our work on this, we have been developing educational exercises for high school students for Earth and Space Sciences curricula, based on, how water is an amazing substance that can influence all kinds of different things, in this case, volcanic activity. If there are any high school educators watching today and are interested in trialing some of our educational exercises, I'd love to hear from you, fagents@hawaii.edu, because we're definitely interested in forming partnerships with local educators. So there's the training of the new generation of scientists as well that comes out of all of this.
So what would you recommend? Because, we're always hearing in the news how, America is behind on science, how we're not, every measure, and how so many of our scientists are coming from other countries and studying at our universities. And you've stayed for 13 years, but many people end up leaving. And what can we do? If you're someone who's young and interested in science, what would you recommend they go and study? What would you recommend they, any suggestions?
Yeah, I mean, if you're interested in science, whatever branch of science you want to go into, you can't do anything wrong by getting math under your belt. Math is important to all sorts of aspects, and I know people don't necessarily want to hear that, but I'm here to show you that math can be fun. Math, physics, chemistry, the basic sciences, they're used wherever you go on from there. So I definitely recommend that. If you are a high schooler or beginning your undergraduate career, seek out professors at the university to do internships with, do research projects with, both the National Science Foundation and NASA, which is where I get a lot of my other funding to do planetary research. They are keen on us scientists passing down the fruits of our knowledge to the new generation. So we are always open to partner with undergraduates or even high schools to help get the youngsters started in research and get them inspired by what you can do with research.
And this is so important because a lot of times the lower levels of math and science are quite boring. So, just algebra and trigonometry, and they're not very, you can't see the beauty in it until you get to the farther down. I mean, when I had to take calculus, I didn't understand any of the math I learned up until then, until I was taking calculus. I was like, oh wow, this is how it's applied.
Right.
This is, what we need to know how to use these numbers. And I think that's a big problem with a lot of students today where, their schools don't have strong mathematics programs, or, they go, oh my God, I'm gonna have to take Chem 3. I'm not gonna go down this route. But it gets more and more beautiful and interesting the farther along you go.
And I think this is where Earth and Space Science curricula are so valuable in schools, because there's the opportunity there to show the students why you do math and physics and chemistry, because Earth Sciences brings all of these things together. So one of the things we're trying to do is show how studying something like volcanoes, which to me is really exciting, relies on these basic building blocks, the math, the physics, the chemistry, and then you can make it seem just much more relevant to the student, why they have to study these things.
What was the hardest class for you?
I think physics, actually.
Yeah?
And I think I sort of ran towards physics because I did find it so much of a challenge. It just was the thing that taxed me the most, and that's why I sort of followed that up.
So we only have a few minutes left. What are some things that you really want to share with the audience before we have to wrap up?
Okay, couple minutes, I guess. I could give you a quick update on the Mars 2020 mission. I'm a co-investigator on the MASTCAM-Z camera instrument, which will be flying on the mission. It launches in 2020 in the summer. It goes to Mars, takes about 8 or 9 months. We'll get there in 2021. And we are currently in the sort of design phase. It's a lot of engineers working like crazy in the background to design the instruments. And we had a preliminary design review in the last week or so, which I think went very well for our cameras. We have another review next year, after which we get to actually really build these cameras. So it's all focused on, okay, do we have the right filter sets? What is the lens configuration going to be? These cameras are based on the current cameras that are on the Curiosity rover on Mars, but they're improved by having a zoom capability. So we can get in very, very close to see very minute detail at rocks, and also zoom out and look at the background and the horizon and what have you. So the engineers are working like crazy on that at the moment, and it's all going very well. And the other aspect is we are going through the process of whittling down potential landing sites. This is a community-wide effort, and over a period of years, everyone gets to have their say about why you should go to their particular pet site. There was a workshop over the summer to cut down the list of candidates to about 8. And these are sites that will have potentially habitable environments and potential biosignatures, signatures of life that had developed microorganism type life. So we're looking at some exciting locations that will have provided environments where life could develop, where it can have been preserved and concentrated. So some of the most favorable sites are these lakes hosted within impact craters with channels that run in that would have brought sediment into these areas to make it a very fertile ground for life to have developed. So that's currently what's going on with the Mars 2020 mission and our particular instrument as well.
All right, and before we sign off, what's your email again, so any educators or any interested listeners that want to can contact you?
Yes, my email is Fagents, my last name, @hawaii.edu. And please do feel free to get in touch. We're going to have exercises and other materials available on the website very soon.
Excellent. This is cutting edge stuff. I mean, this is really great that you're doing this. But thank you so much for coming on our show today.
You're welcome.
We've enjoyed it, and I'm sure everyone listening has enjoyed it. Again, I'm your host, Hilary Weinberg, filling in for Jay Fidel. Tune in every Monday at 1 p.m. for Research in Manoa, and we'll see you next week.